Okay, let's dive right in. We're going to get to grips with the bedrock of orthopedic surgery, biomechanics. We're going to talk about how bone and the implants we use to fix it actually behave when they're put under load. And trust me, this isn't just dry theory. This is the fundamental science that really dictates whether an operation is going to work or not.
So let's kick things off with a question that really gets to the heart of what we're talking about today. You know, a surgeon can take a metal plate, bend it in their hands, and shape it to fit a bone perfectly. But if you tried to do that with a ceramic hip head, it would just shatter into pieces. Why is that? Well, the answer is all wrapped up in the basic properties of these materials, which we're about to break down.
And here's our game plan. We're going to start with the absolute basics, the language of force, stress, and strain. Then we'll follow a material's journey as we load it up, from that initial springy, elastic bending to the point where it deforms permanently. We'll nail down the difference between strength and toughness, and then we'll tie it all together in the real world of bone, implants, and biology.
All right, first things first, before we can talk about how things bend and break, we need a common language. And that language is built on three really core ideas: force, stress, and strain.
So let's start with stress, which we show with the Greek letter sigma. Now, you can think of stress as the concentration of an internal force. See, it's not just about how much force you're putting on something, but how spread out that force is. By dividing the force by the area, we get this standardized value. And this is incredibly useful because it lets us compare, say, a thin metal wire and a thick metal rod made of the exact same material. It's all about the force per unit area.
Now, if stress is the cause, then strain is pretty much the effect. Strain, or epsilon, is just how we measure how much something deforms. And just like stress, we standardize it. We look at how much the length has changed, and we divide that by its original length. What we get is a simple ratio, basically a percentage, that tells us exactly how much an object has stretched or been squashed.
And here it is, plain and simple. You've got an object, it has its original length, you apply a force, and it stretches to a new length. Strain is just that little bit of change divided by where you started. It's a really elegant, simple way to put a number on a change in shape.
So now that we have our terms down, let's see what happens when we start to apply a little bit of load to a material. We first enter what's called the elastic zone. And this is the zone of temporary, and this is the key word, reversible change. And that brings us to what is, without a doubt, the most important graph in all of material science, the stress-strain curve. We've got stress going up the side and strain along the bottom. And just look at that first part of the curve. It is a perfectly straight line. This linear, straight-line relationship is the absolute signature of the elastic zone. This straight-line behavior is described by a really famous principle called Hooke's law. And all it says is that for a while, the more stress you put in, the more strain you get out in a perfectly proportional way. That E is just a constant that links them. The most important thing to remember here is that as long as you're in this zone, the material behaves just like a perfect spring. You let go of the load and it snaps right back to its original shape. No harm done. Now add E from Hooke's law, that's called Young's modulus, and it is a massively important property. It's simply the slope or the steepness of that initial straight line. And what it represents is a material's stiffness. So something with a really steep slope, like a ceramic, has a high Young's modulus. It's super stiff and it really resists being deformed. On the other hand, something with a shallow slope, like a tendon, is much more flexible and has a low Young's modulus. But what happens if we keep pulling? Well, eventually we leave that nice, safe, elastic zone and we cross a threshold. This is the point of no return, where any deformation we cause becomes permanent. We call that threshold the yield point. It's the exact spot on our curve where that straight line starts to bend, and the amount of stress it takes to get there is the material's yield strength. Once you've pushed a material past its yield point, you have fundamentally and permanently changed its internal structure. You can't go back.
This irreversible change is what we call plastic deformation. The material is now permanently bent or stretched. Now that might sound like damage, and in a way it is, but in surgery we actually use this to our advantage. When a surgeon contours a metal plate to match the curve of a bone, what they're doing is intentionally pushing that metal past its yield point into the plastic zone, so it takes on a new, permanent shape that's perfect for the patient.
Okay, so we've stretched it elastically, we've bent it plastically, but what if we keep going? Let's keep applying that force and see what happens as the material heads toward total failure.
As we keep deforming the material in that plastic region, the stress needed keeps rising until it hits a peak. This peak, right at the top of the curve, is the ultimate tensile strength, or UTS. That is the absolute maximum stress the material can handle. Any point beyond this, and the material starts to get weaker and thinner in one spot, heading inevitably towards breaking.
Now let's talk about energy, because this is really cool. The area underneath our stress-strain curve actually represents the energy the material absorbs. So resilience is just the area under that initial straight elastic part. Think of it as the bounce-back energy, the energy you can store and then get back. Toughness, though, toughness is the total area under the entire curve, right up until it breaks. It's the total amount of energy a material can soak up before it fractures. And this is a key point. A material can be strong, meaning it has a high UTS, but not very tough if it just snaps without deforming much.
So these ideas, plastic deformation and energy absorption, let us sort materials into two really important camps, and understanding the difference between these two brings us right back to our very first question, why do plates bend and ceramics shatter? So on one side, you have brittle materials. If you look at their stress-strain curve, they have a nice elastic region, but then, bang, they fail suddenly with almost no plastic deformation. Think about glass, or our ceramic hip heads, or even PMMA bone cement. On the other side, you've got ductile materials. These guys have a huge, obvious plastic region. They can stretch and deform a whole lot before they finally break. And that's why a metal plate is ductile, so we can contour it, while a ceramic is brittle and would just fracture.
Now, this whole concept applies perfectly to bone itself. Just look at the difference here. On the left, you've got healthy, cancellous bone. It's this dense, interconnected web. Then on the right, you have osteoporotic bone. It's porous, the struts are way thinner, and a lot of those connections are just gone. You don't even need the graph. You can just see how this is going to change how it behaves mechanically.
And here's exactly how those structural changes cash out in terms of mechanics. Compared to normal bone, osteoporotic bone is less stiff. It's weaker, and it's less tough, meaning it can't absorb nearly as much energy before it breaks. But here's the kicker. It also becomes more brittle. It fails with less warning, and that is precisely why someone with osteoporosis is so much more likely to fracture a bone from a simple fall.
Okay, let's pull all these threads together now. How does understanding stiffness and strength and ductility actually help us pick the right bits of metal and plastic to fix the human body?
Well, this table really lays out the fundamental challenge in orthopedics. Just look at the Young's modulus, the stiffness of things like cobalt chrome and titanium compared to bone. They are just way, way stiffer than the cortical bone we're screwing them into. And that mismatch is not some small detail. It's a massive deal.
And that big problem has a name. It's called stress shielding. Because that super stiff metal implant is so much more rigid than the bone, it ends up taking almost all of the load. The bone underneath is shielded from the healthy stress it needs to remodel and stay strong. And what happens? Well, bone follows a simple use it or lose it rule. It starts to get weaker, it resorbs, and that can lead to the implant getting loose and ultimately failing.
So, there you have it. We've walked through the entire journey of a material under load, from a little bit of springy bending to catastrophic failure. We now get why a ductile plate can be shaped to a bone, while a brittle ceramic just can't. But the story doesn't really end here with these static properties. See, bone isn't just a material. It's a living tissue that is constantly changing. The very same stresses we've been talking about are the signals that tell bone to get stronger or weaker. And that incredible, dynamic process, well, that's known as Wolff's Law. And that's a story for another time.